So one of the ways that we can improve counting our k-mers is perhaps by using multithreading. After all, if I'm just counting substrings, then there should be no reason why I can't parse that out. There's no calculation that's dependent on the previous one except the counter. So if I could come up, for example, with a dictionary where multiple threads can access that dictionary, and a thread can say, hey, I need to increment the counter for this particular dictionary. I want to just grab that, I'm going to lock it for a second, and then I'm going to increment the counter, and once I'm done, I'll release the lock, and if you want to increment the counter, you can do that. And so we could do multi-threading with locking. It turns out that this is about the most useless way that you can count strings, because every thread ends up waiting for the lock. And you just end up spinning, wasting time aimlessly. And so instead of using locking, maybe we can use a slightly more modern technique that's called compare and swap. The way that compare and swap works is that we have a function. Let's say it's going to return an int, and we'll call it compare and swap. And the function takes 3 arguments. It takes a location, and that's basically our location in our dictionary, right? Based on kind of the hash code. It takes the old value, and it takes the value that you want to insert. And so if you're writing a counter, then basically what you do is you say, tell me the value at this location. Okay, I'm going to increment that by 1. And then I want to do a compare and swap at that location. Here's the old value plus 1. Okay? And the way that compare and swap works is we read the current value from location. So we read what the current value is. Now we say if the current value is the same as the old value, what that means is that the location hasn't been updated by another thread. So if that's true, then I'm going to set the value at location to the new value. Once I've done that, all I'm going to do is I'm going to return the current value. So if you give me a location, you give me the value that you think is currently in that location, and you give me the new value that you want to add, then what I'm going to do is I'm going to read the location, and if the current value there is what you told me you think it is, sweet, then I'll just increment, I'll set your new value at that location. If it's not what you think it is, what I'm going to return you is what the current value really is. So if between you reading it and you asking me to set it, some other thread changed the value, then I'll tell you what the new value is. Now it's up to your code to check the current value that's returned and say, is the current value the same as what I thought it was? If it was, then I know that compare and swap has placed my new value in the location. If it's not the same, then I need to increment my old value and update it and try again. And I need to keep trying until the value that's returned is what I think old value is. Now the beauty of this method is that in pretty much every kernel that's been written for a long time, but even nowadays in hardware, in fact not just nowadays, for quite a long time, there are hardware implementations of compare and swap that you can use. Compare and swap is guaranteed to be atomic. What that means is that once you call the routine, while that routine is happening, nobody else can make a change to that value. It's guaranteed to be atomic. It's guaranteed that if you give me an old value and a new value, and I read the same old value, then I'll set the new value. Whatever else is trying to access the same location will have to wait until I'm finished for this to happen. But this is a lock-free approach. It doesn't require a locking mechanism. It doesn't require a mutex or something like that, which I have to request. I say, give me the lock. Okay, I've got the lock. I'm going to update the counter. Here's the lock back. This is an atomic one-step approach, and it's very fast.